Okay, so it's my pleasure to introduce Aria Halavati from Courant Institute. We'll talk about the decay of excess for the abelian Higgs model. Go right ahead.
Okay, thank you. Thank you so much for the introduction and the invite. I'm very happy to be speaking here and the fact that it's online, that it can reach as many people as possible. Great. We also have less carbon footprint, better for everyone. So the title is Decay of the Excess for the Abelian Higgs model, and it's a joint work with my advisor Guido de Philippis and my friend Alessandro Pigati. And the title is a mouthful, so I don't expect anyone to know anything about what are these models. So I'm going to try to motivate it. So the talk is going to have two parts. Basically, the first part is some backstory, and the second part is what we did and some heuristic ideas and a lot of hand waving. Okay. So the main theme of the things that we're going to investigate are interfaces and concentration sets. So basically, there are a lot of physical phenomena that their mathematical models lead to the understanding of things called interfaces and concentration sets. And they're basically the place where the phase transition happens or the phase changes from one to the other. And you can think about it or as the boundary between, say, the two phases. Okay. And they typically have a fixed codimension which is basically the dimension of the state space. And a lot of these models, which are basically extremizing some type of energy, have a term in them that prefers some type of ordered transition. And this order, a lot of times, turns out to be geometric in nature. And geometry actually helps reveal a lot of interesting things about these models. And if you're lucky, these models illuminate sometimes interesting consequences that are hard to obtain by pure geometric methods. Okay. So the first part of the talk is the story of codimension one, basically the Alencon model. Okay. So the Alencon model has a phase parameter u, which takes values between -1 and +1. And you can think about this omega to be basically a container that is mixing water and oil, right? And the values u equal plus and -1 correspond to pure states. So if you're just water or just oil, and the set where u equals 0 represents, say, the interface between water and oil, right? And note that it has codimension 1. And if you want to think about this more precisely, you should think about the set where u is bounded away from these two ends to be somehow the diffuse transition between the two states. And the energy takes basically the following form. So there is the Dirichlet energy, our favorite energy, and there's a potential, right? So this Dirichlet energy is the one that is actually favoring the order transition. And this potential favors being a pure state, right? So you can see that if u is ±1, this potential is exactly 0, right? And doing very simple computation, you can see that the stationary points satisfy the following semilinear PD, just called the Alencon PD or Alencon equations, okay? So first, I want to show you a little bit of how the picture is going to look like and what you should expect this model to behave. So think about this omega to be a very, very large container, possibly all of Rn, right? And one should imagine this domain to be very large. Doing a little bit of iteration and Moser iteration arguments, you can see that the energy exponentially decays away from this zero set, right? Or this transition layer. So the expected picture is that U is close to being a pure state away from a strip of thickness 1 around the zero set. Okay. And in this strip of thickness 1, the energy is actually concentrating, right? And instead of the domain to be very large, you can actually rescale this down and rescale U down with it and also the energy. And you can think, and you're basically looking at the minimizers of the following rescaled energy. You can think that epsilon is basically a very small parameter. And thinking about the exponential decays of the previous slide, if you rescale everything down, you can see that U actually converges to plus and -1 as epsilon goes to 0. So this transition becomes sharper and sharper, right? And you see a picture like this, okay? So say on the top, there's like oil, on the bottom, there's water, and you have an epsilon thick layer of basically this diffuse transition, right? You can do another analysis. So think about this energy, do an AMGM or Young's inequality, okay? And perform a co-area formula, you can see that this energy is actually lower bounded by a weighted average of the areas of the T level sets, right? And if you can convince yourself that all of these level sets live close to each other in near that region of the zero level set, somehow this energy is lower bounded by some constant, which is just the integral of this times the area of the zero level set, right? So then what you expect is that minimizing this energy should be very related to minimizing the area, okay? And in particular, if the above achieves equality, so think about a point near the transition layer, the gradient points in the normal direction, right? And if you think that these two energies are balancing, basically, the AMGM inequality is an equality, you can see that in this normal direction, you're solving an ODE, right? So basically, you're putting a bunch of solutions of this ODE in the transversal directions, rescaled by epsilon, right? And the solutions of this ODE basically look like tangent hyperbolic, right? So all of this hand waving is to convince you that this energy is related to minimal surfaces, right? And in fact, this is rigorous. So you can see that this energy, as epsilon converges to zero, gamma converges to the perimeter functional. What is gamma convergence? Basically, it means that minimizers of the Allen-Kohn energy converge to minimizers of the perimeter function, right? And in fact, you can say even more. You can say that actually stationary points of this energy converge to stationary points of the area functional, which is just mean curvature 0. Gradient flows converge to gradient flows of the area functional, which is basically mean curvature flow. And actually, most non-degenerate minimal submanifolds can be recovered as limits of this Allen-Kohn energy. And a lot of minimal surfaces in three manifolds with desirable properties can also be constructed with min-max for this Allen-Kohn. And basically, min-max for Allen-Kohn is much easier than, say, the Almgren-Pitts setting, right? It's just min-max for semi-linear PDEs. So all of this, and by the way, if you have any question, feel free to interrupt. So all of this is to convince you that the behavior of this zero level set in the large scale is described by minimal surfaces, right? So then you can start asking the question, does this do these level sets actually inherit anything more from minimal surfaces? And what do we want them to inherit? You can choose your favorite type of property, but here we want rigidity. Okay. So let me give you examples of rigidity in minimal surfaces. So one of them is actually a very classical result due to Allard, which basically says that if you have a k-dimensional minimal surface where its energy on very large balls is very close to the one of the flat plane, right? Then it should be flat. Okay. You can think about this as some kind of Liouville type theorem for harmonic functions. Okay. And these kind of entire classification results are very deeply connected to local regularity results, and also in this case. And this resulted, in fact, the consequences of the local one, which says that if on a ball of radius 1, you're very close to, on a ball of radius 1, your area is very close to the one of the flat plane, then inside you're a perturbation of the flat plane, right? And in fact, the C1 alpha perturbation with a epsilon bound on the C1 alpha norm, right? Okay. For the case of hypersurfaces, in fact, you can even say more. So, and these are called Bernstein type theorems. So think that you have a complete embedded codimension 1 minimal hypersurface. Then this minimal hypersurface is flat if it's a graph and dimension is less or equal than 8, or if it's stable and dimension is less or equal than 6. And of course, dimension bigger than 8 doesn't hold because there is a counterexample called the Simon's cone. Okay. So one can actually start asking the question that, okay, does a property like this hold for solutions of Allen-Kohn, which was in fact the conjecture of de Giorgi, which says that, okay, think about you have an entire solution of Allen-Kohn where it's monotone in one direction, right? So if it's monotone in one direction, it basically means that the level sets are graphical. And does it hold that it should be one-dimensional? Basically, after a possible rotation, U just depends on one dimension, where this G is just a solution of the ODE in that, say, perpendicular direction. And of course, provided the dimension is less or equal than 8, because you don't expect anything to inherit anything that minimal surfaces don't have, right? Okay. And after a lot of partial progress, Ovidiu here was actually able to prove this version of the George's conjecture, which was a slight added assumption where if you assume that the limit of U is plus minus 1 as you go away from this plane of xn equals 0, then you are in fact one dimension. Okay. And this assumption basically tells you that if you have an entire critical point with these two assumptions, you get that it's actually a minimizing. Okay, and then you can just do you can use the locally minimizing property to gain some information. And in 2015, Kelly Wang was able to get a type of an Allard rigidity result for these equations. And this, in fact, implies Ovidiu's result with just very simple compactness arguments. So basically, if you have a solution where in large balls, there's a limit of R missing here, but if you have a solution such that its energy on large balls is very close to the one of the flat solution, then it should be flat. Okay. So this is in the spirit of this Allard rigidity, right? And the ideas of the proof, I'm going to go over just like the overview of the ideas of the proof, basically with a very simple compactness argument and using Allard or Bernstein or whatever property you have for minimal surfaces, you can see that blowdowns are basically flat, right? And blowdowns of entire solutions being flat, it means that on larger and larger and larger balls, your configuration is very close to being flat with respect to a possibly changing plane, right? So this is the first step. The second step is to gain an improvement of flatness. Okay, so what does it mean to have an improvement of flatness? Very vaguely, it means that if the configuration is very close to be flat at scale 1, then it is much closer to be flat at scale half. Okay, and then you iterate this, and then you either get your classification results in the case of entire, or you get your regularity results in the sense of Morey Campanato, the characterization of Holder spaces, and you get regularity results, right? And also here, closeness is measured in different ways. So that depends on what kind of problem you're working with and what tools you have available to actually attack this problem, right? But there's one intuition shared between all of these kind of improvement of flatness ideas, which is that the area functional actually linearizes to the Laplace's equation. So how does it linearize to the Laplace's equation? So think about U. U is different from the U in the Alencon. I should have changed it to an F. My bad. But think that your minimal surface is given by a graph. And basically, this is the area functional. This is basically the area of a graph. And if you think about the Taylor expansion of 1 plus x squared, square root, you get that it's this up to first order, right? So if you minimize the area, you kind of expect to be minimizing 1 plus the Dirichlet energy, which is basically just minimizing the Dirichlet energy. And minimizers of the Dirichlet energy are just harmonic functions. And the main difficulty is to make this linearization actually rigorous, right? So actually make this rigorous to be able to pull back the decay estimates you have for harmonic functions to the problem that you're working with now, right? So a bit on Ovidiu's toolbox, and you can correct me if I'm being imprecise, but I know that his results rely on a viscosity type technique and partial Harnack type estimates. Basically, he proved that you can get a sort of decay of oscillation for the zero level set, and this closeness is being measured in like an L infinity way, right? And to my understanding, this toolbox relies heavily on maximum principal type arguments and building comparison functions, which are scalar in nature, at least in these diffuse settings of minimal surfaces. So at least in these diffuse settings, codimension 1 is essential for this toolbox. And we weren't able to apply something like this for codimension 2. could be our failure, but really we didn't find anything similar to this for the problem that we're studying. Okay, getting ahead of myself. So I'm going to tell you a bit of the story of codimension 2. So think you want to do the same, but with instead of codimension 1, with codimension 2. So you increase the dimension of the target space, the first naive attempt. So instead of R, you take it to be R squared. And instead of R squared, we take the complex numbers, and which leads us to the model called abelian Higgs, or Ginzburg-Landau, or Yang-Mills Higgs, or U1 Higgs. There's a lot of names, depends on which background you come from. So the model takes the following form. So the form looks a bit complicated, but I'm going to try to motivate each of the terms. Okay. So first, you have your order parameter, which takes values in C now, right? So the target space increased in dimension. You have a vector, right? And the Ginzburg-Landau energy takes the following form. So we call this U order parameter. And where U is equal 1, you reflect the pure state. So this Ginzburg-Landau energy is trying to model superconductivity. It first comes from physics. And where the modulus of U is exactly equal to 1, you kind of say that you're superconducting there. And this, if modulus of U is away from 1, it's kind of like a density of, they say Cooper pairs, or you can just say superconductivity, or just being away from pure states. And A is the magnetic vector potential. So this first term is again a Dirichlet energy, but it's twisted by this A, right? This second term penalizes how much A twists. And the third term is just a potential. And this kappa is just some parameter that we're going to fix later on. Okay. So first, when you look at this energy, there's one thing that you notice, that this energy has a huge group of symmetries. In fact, if you twist A with an S1 valued map, e to the I theta, and also you twist, if you twist U, and if you twist A accordingly, the energy remains exactly unchanged. If you do a little bit of computation, right? Because curl of D vanishes, and the modulus just remains invariant, and these two terms kind of cancel out each other, right? So these two pairs are indistinguishable, at least at a variational level, right? So whenever we're going to solve this equation, or we're talking about solutions of this equation, I always say up to a gauge equivalence, right? So we fix some gauge. So a lot of times they call it the Coulomb gauge, or whatever gauge you want. There's basically a huge group of freedom. So this is in 3 dimensions. And in fact, in higher dimensions, there's a more covariant formalism of this energy, which is in the setting of complex line bundles. So what is a complex line bundle? A complex line bundle is basically a twisted Cartesian product of some manifold with the complex line or complex numbers, right? And what do I mean by a twisted Cartesian product? In the same sense that the Mobius strip is a twisted Cartesian product of R times S1, right? So locally, you are actually a Cartesian product, but not globally. And then U plays the role of a function, which is a section, and this nabla, which is basically a metric connection, or that twisted gradient. And the energy takes this following form, with this F is the curvature of this connection. If you're not comfortable with this, you can actually look at this energy locally and actually write it as a Cartesian product of complex numbers with some open set of this base manifold. You see that, you get a local trivialization. So you get that actually this connection is the gradient minus some twist with some one form, right? You get a twisted Dirichlet energy. You get the exterior derivative, which is a 2 form, and you get this potential. Okay. So here, the transition layer, instead of U being away from +1 and -1, the same role is played by the gauge invariant vortex sets. So I'm gonna call it vortex sets a lot of times. But I just mean basically the transition layer. And it's basically of codimension 2. I'm going to convince you later on, but the picture basically is going to look something like this. So in the same setting, but you're basically a tube around a codimension 2 object, right? And away from this tube, you're close to be pure states, right? And you can think about if you rotate around the boundary of this circle, your U has like a prescribed rotation number, right? And because of just topological restrictions, you have to assume 0 at somewhere inside this tube, right? So a little bit of background on this energy. In the case where there is no magnetic field, this energy is actually just called the Ginzburg-Landau energy and has attracted a lot of attention in the recent past, and it's quite difficult to analyze. One of the reasons is that the energy localizes very, very slowly. So if you think that on this slice you're an S1 valued map, actually, you have a contribution coming from the gradient of your phase, right? And the gradient of the phase, if you just think about e to the I theta, the gradient of the phase is of order 1 over r, right? So the gradient squared of the phase is 1 over distance squared. And if you integrate this on one of the slices, excluding, say, the vortex set, you get log epsilon of energy. So energy concentrates really, really slowly. And you get that concentration phenomena that we have before, but it's much more complicated to derive. And also, since you get that energy localizes slowly, and in fact, energy comes from these dyadic annuluses away from the vortex set, you get that vortices. Basically, if you slice this two-dimensionally, if you have two of these vortexes near each other, they kind of repulse each other with an energy of order log of the distance. So this means, with a lot of analysis, that because of this interaction, integrality of the limit submanifold is not really guaranteed. You can have two vortexes twisting around and approaching each other diabolically to get you like 2.5 multiplicity in the end instead of 2, right? And this is in fact proved rigorously. So integrality of the limit submanifold is not guaranteed. It is guaranteed if you have less than 2 vortexes, and there are counterexamples for 2 vortexes in all dimensions. Okay. But the case that you have a magnetic field is very special, and it's really nice because the twisted Dirichlet energy tames this phase. So basically, this one form kind of goes against this D of the phase and helps you and helps us to cancel out the energy that you're getting far away from this vortex sets, right? And there is also something much more beautiful when kappa is equal to 1, which is actually a classical observation due to Bogomolny, is that if you think about this energy in just 2 dimensions, so basically it's the same when we're thinking about the Alencon solutions for just the ODE in 1 dimensions. If you do a completion of squares, you can see that this energy is a topological constant, thus a positive integral. Okay. And first, you want to study minimizers of this energy, right? So minimizers of this energy, you expect, before I say that, this n is basically the vortex number or the winding number of U at infinity, okay? So when you want to study the minimizers of this problem, first you put this equal to 0, and you see if you can get anything. And these are actually called the vortex equations. So after choosing an orientation, basically a plus minus, the vortex equations are of this form. There's like some kind of nonlinear conformal equation in this first one, and the second one is just some potential balancing with the curvature. And this was actually the content of Clifford Taubes' PhD thesis, where he proved that, first of all, first order and second order equations are equivalent. So all stationary points are minimizers. So if you want to study stationary points of this energy in 2 dimensions, you just have to study first order equations. It's very analogous to the case of Alencon, where you have just the ODE, right? And after you prescribe the 0 sets, counting with multiplicity, the solution is unique, right? So basically, the minimizers of this energy behave like non-interacting vortices, right? So, and the energies with n vortex is exactly equal to 2 pi n, right? Saying if n is a positive number. For reasons that I'm going to convince you later on, was necessary for us as a toolbox to improve these uniqueness results to some quantitative stability, right? And which is as follows. So basically, your distance with the moduli space of these solutions is controlled by how minimizing you are, right? So, and the only assumption you need is that you're very close to actually being minimized. There's no regularity assumptions. And I'm not going to talk about this too much, but just the fact that this power 2 is really essential. So if you get any power less than 2, for the results that I'm going to show you later, dimension restriction comes in. And basically, just a glimpse of the ideas is that if you write this discrepancy, you can see that it takes the following form, if R is the modulus. And it turns out that a kind of a weighted Hodge decomposition was really useful to deal with these two energies. And basically, Hodge decomposition is equivalent to elliptic estimates. So weighted Hodge decomposition, you need weighted elliptic estimates, which were not known before. So they had to be developed from scratch, are in the spirit of Kaffer-Licon-Nirenberg type inequalities. And with those techniques, we were able to obtain a quantitative stability of this. And a glimpse of those inequalities, you can just think about this special case. I don't think this was known to experts before, but there is, and the proof is very simple, and it's just Stokes' theorem over and over again. It's one of the exercises of Evans. And if you actually really go nuts with that exercise, you can see you can extract better things. Anyway, so in the sequel, I'm going to take kappa just equal to 1, right? And I'm going to show you, we were going to do, again, the rescaled picture, right? So instead of thinking about the domain to be very large or entire solutions, rescale the picture down. So basically take a rescaling of your pair, right? And the energy takes the following form, right? So you're thinking about omega to be a fixed domain of, say, size 1, and you're looking at stationary points or minimizers of this energy. Because of this taming of the, say, magnetic field or this twisting of the Dirichlet energy, you get good exponential decay from the vortex set, which is as follows. And the expected picture, which was the one I showed you before, you get exactly the behavior you were expecting, and you get very good concentration in the vortex set. And analogous to Alencon, you can actually say that as epsilon goes to 0, these functionals converge in a suitable sense to the n-2 area of the 0 level set, right? So there is the gamma convergence, there is the gradient flow convergence, and there is the convergence of stationary fields, stationary pairs. To be more precise, if you look at these energy measures, so if you name these energy measures little e epsilon, these energy measures converge subsequently to a codimension to integral varifold, a stationary codimension to integral varifold. And the currents dual to these Jacobians converge to an integral cycle, which has an energy bound, right? So basically, the cancellation happens in this, but it doesn't happen in this, right? Okay. So now if you're convinced that for these equations, the 0 set behaves like a minimal submanifold in the large scale, as before, we can ask, do they inherit any rigidity? And the answer is yes, which is actually the title of the talk. So we were able to obtain an Allard type rigidity for these kinds of solutions. Okay, so in dimensions up to 4 for an entire stationary pair with energy close to the multiplicity 1 regime. So you should think of this as the Allard regime. So in the large scale, your energy is very close to just putting a one vortex solution constant in tangential directions, right? So if your energy is very close to the multiplicity 1 regime, then you're necessarily two-dimensional. So if your energy is close to be flat, then you are flat, right? And this 2 pi is the energy of a one vortex solution, okay? And for minimizers, we can remove the dimension restriction because we have just variational techniques and we can construct competitors. So basically, if you have the same criteria, so if you have the same assumption on the energy, you get that you are actually necessarily going to be two-dimensional, okay? So first, I want to give you a little bit of ideas of the proofs. There's going to be hand waving and there's going to be pictures. So But to start, first I have to tell you how we measure flatness. So the flatness is actually measured in two ways. If you expect to be constant in tangential directions, then you expect the tangential part of the energy exactly to be zero, right? So we measure this in XS1. And if you expect on two-dimensional transversal slices to be a solution of the vortex equations, then you expect this to be zero, which is exactly how we measure XS2, right? To draw parallels between the theory of integral varifolds and integral currents, this XS1 is parallel to the notion of the quadratic excess in the setting of integral varifolds. And this full excess, and this XS1 doesn't depend on orientation. If you see that if I flip 1 and 2, this integral does not change. But if I flip 1 and 2, there is a plus minus sign that is changing, right? Okay. So this E1 is parallel to the notion of excess in the theory of varifolds, and their sum is parallel to the notion of excess in the setting of integral currents. And you can see there's a similar formula in the setting of integral currents. So basically the mass of the current is the mass of the flat ball plus the full excess plus a very nice exponential error, right? This exponential error is as small as if you want it to be. Doesn't break anything down in our arguments. Okay. So now the idea is, again, we can see that this, again, like before, we can see that on large and large balls just by applying some compactness argument and Allard. You can see that you're flat with respect to a possibly changing plane. Now the idea is prove some kind of excess decay. Okay. And this is the content of the first theorem of the excess decay. So this concerns just solutions, right? So all solutions, I mean. So the only assumption you need is just to be a solution. So in all dimensions, if on a large ball you're in the multiplicity 1 regime, then the XS1, so basically just the variable type XS, decays in a smaller ball, or it was already small to begin with. Okay, so you basically, in the entire case, when you want to iterate, you iterate as long as you hit this threshold, right? And two things that I want to mention is that first, unfortunately, for solutions, we can say only E1 decays. We can't get the full excess to decay. This is one of the reasons that the dimension restriction comes in. And the other reason is that you can see that if you iterate this from larger and larger balls, you can see that the pre-normalized excess on large and large balls is small o of r to the negative 2, right? So if they renormalize this small o of r to the negative 2, and you're renormalizing by n r to the n minus 2, you can see that the full integral is small o of r to the n minus 4. So that's how you get classification up to dimension 4. And this also affords us somehow a diffuse kind of regularity. So you can say that also the zero set, if you iterate and stop at scale epsilon, you can say that the zero set lives epsilon close to a C1 alpha graph, which is going to be used later. For solutions, actually, we get the same thing with two improvements. One is that for any beta, you can find thresholds. So basically a small tau and a large enough scale such that your full excess decays until you hit this 1 over r to the beta, right? So this is valid for any beta. So for any beta, basically this becomes small and this becomes larger if you take beta larger and larger. So if you just take beta bigger than n minus 2, you get the classification for entire local minimizers, right? And the other thing is that you can see that the full excess decays. And this is because you want to do basically because you have comparison arguments available to you when you're looking at locally minimizing solutions. So I'm going to show you ideas of these proofs, just a glimpse of some of the ideas. So first, again, you can see that the configuration is flat on large scales with respect to a possibly tilting plane. And then we want to linearize this in the regime where the radius is becoming very large and excess is also vanishing. So equivalently in the rescale picture, where excess is vanishing and epsilon is also vanishing. Okay. So to do this linearization, we want to do somehow a Lipschitz approximation of the zero set, of these level sets. The first difficulty is that, so if you read Kelly Wang's work, when he was doing this Lipschitz approximation, he actually chose exactly the zero sets as the graphs that he was trying to Lipschitz approximate, right? But the level sets are not available to us in this setting because of exactly gauge invariance. The level sets are just not well defined, right? So the idea is that you take this Jacobian. So this Jacobian is actually converging to just a flat line, right? So you take this Jacobian and then you slice it in the transversal directions. So on top of each point in the base tangential directions, you get a measure, right? And this measure kind of looks like an epsilon modified Dirac near the zero set. So you take the barycenter. And this barycenter, because it's a barycenter of the slices of this Jacobian, just by slicing formulas, you can get BV estimates on these barycenters, right? And because of just classical BV theory, if you perform a Lipschitz approximation, you get Dirichlet estimates with respect to XS1, okay? So you kind of Lipschitz approximate the barycenter of these Jacobians, right? Then the next idea is a harmonic approximation. So how do you want to perform a harmonic approximation? Basically, you see that if you perform inner variations, you get a stress energy tensor that is row-wise divergence free, right? Which is basically a symmetric matrix that is row-wise divergence free. Don't worry about this complicated form. It's just a matrix that is basically row-wise divergence free. Because of the structure of the XS2 and XS1, this self-duality or this vortex equations, this Jacobian is very closely related to the stress energy tensor, at least on some off-diagonal elements. Okay. So you expect to relate the slices of this Jacobian to the divergence-free condition of this, and you get this equation. It's basically an approximate elliptic equation in the sense of W -1 infinity, right? And if you combine this with the Dirichlet bounds that you got from just the slicing formulas, you can see that in the spirit of just classical Allard regularity theorem, you can see that, okay, these barycenters are harmonically approximated with a small o of XS1, right? So if you just renormalize this phi by square root of XS, this bound becomes O of 1. And in this bound, XS1 just drops out, right? And you just do Relic compactness. Okay. So now you see that the barycenter is harmonically approximated, and harmonic functions have really good decay estimates. Okay. So you can see that up to a tilting, you can make your height of the barycenter decay. So how do we conclude after this? We use the stress energy tensor to derive a Cacciopoli type inequality, which is exactly an excess height bound. And since height decays, you can see that excess decays. And where does this 1 over r squared come from, or this epsilon squared? Is because when you're trying to do the Cacciopoli inequality, on your right-hand side, you're testing the slice measures with the square of the height, right? So you see that the first term is barycenter squared plus variance. And variance is of O of epsilon squared. And you can improve it to little o of epsilon squared just using quantitative stability. Okay. So you get the theorem 3 of decay of excess for stationary points. Right? So for local minimizers, I'm not, because the analysis is very complicated, it's very involved. I'm just going to give you a visual guide to convince you, and we're just going to pretend dimension is just 3. So a priori, the picture is going to look like this. Okay, so you have some zero set, might not be flat, might not be even regular. Iterating theorem 3, you get some epsilon diffuse regularity. So you know that it lives epsilon near a line, or in higher dimensions, basically epsilon near C1 graph. Okay. you choose a good radius that you cut, and you replace it inside with a line. Okay. So you see that the length of this line decays, right? And you want to mimic this in an energy level and compare it to contradict locally minimizing, right? Or use the local minimizing techniques and comparison arguments. So what you do is you want to mimic the length of this line in an energy level. So what you do is you take a one vortex solution of taus, you rescale it down, and you put it on this line where the zero is exactly on this line. Okay. And you pull it back over all of this line. Now this is still, so the energy is comparable to length inside of the cylinder, right? But this is still not a competitor because we really need to attach to the boundary conditions to be able to have a competitor. But the problem is, so first, if you want to attach to the boundary conditions in this, say, purple interpolation regime, the idea is to basically use the quantitative stability to say that if you sliced it in a place that XS2 was small, you were close to a one vortex solution. So when you attach, it doesn't cost you too much energy, right? But a problem that shows up is that when you want to do this, there is a gauge freedom in this quantitative stability. So you really need to first change the gauge and then interpolate between, say, the pullback solution and the boundary conditions. In this picture, it looks very simple to modify the gauge in a way that the approximation doesn't cost you too much because it's just a slice on the right, a slice on the left. But if you're in higher dimensions, this becomes complicated really fast. And what you do is you do a very delicate gauge fixing argument. And one of the crucial tools was that epsilon diffuse regularity that I was mentioning to you before. So think about this purple region of the interpolation region, blow it up. So you have your zero set, you have your barycenter, then cover it with very thin cylinders. That's epsilon width, epsilon ln epsilon height times beta. So the first thing that this epsilon diffuse regularity gives you is that none of these two cylinders are on top of each other. Okay, this is the first thing. And what you do is that you gauge fix inside each of these cylinders in a really careful way, and then you attach these gauges with a partition of unity. And of course, you should be skeptic of attaching things with partitions of unity. But if we do the gauge fixing in each of these cylinders carefully enough, when you attach them with a partition of unity, it doesn't cost you too much. And in fact, you can attach everything and construct a gauge such that you can, say, attach the pullback solution to the boundary conditions. And why beta epsilon ln epsilon? Basically because away from the cylinder, the exponential decay of the energy gives you epsilon to the beta. And this is where 1 over r to the beta shows up. Okay. And you use a comparison argument and the fact that the mass inside is equal to the mass of the flat ball plus the full excess and the approximation of the length to say that, okay, the excess actually decays until I hit the threshold epsilon to the beta. So in a summary, we were able to obtain rigidity for solutions up to dimension 4. We were able to also obtain rigidity for local minimizers in all dimensions. The case of solutions for dimensions bigger than 4 is still open. There's some hints on how to push further. There's like some XS3 that we didn't write down that connects this XS1 and 2 together. But even in the best case scenario, so there's a PDE that connects XS3, XS1, and XS2. In the best case scenario, you might be able to improve this n equal 4 to n equal 5, which is suggests that maybe if you want to go further, you really need some better tools or maybe some new tools. I don't know, that it's not very clear. And and what I'm interested in as the next steps to this project is basically attacking this problem in all dimensions with just stationarity. In the higher multiplicity regime, just at least just the Gibbons conjecture, and say in just dimensions up to 4 and 3. Does this have applications to geodesics in dimension 3, which seems, to be honest, unlikely because this abelian Higgs provides a really good dictionary for minimal surfaces. So you wouldn't expect to have anything more that you can get with just variables and geodesic nets. And applying this pipeline to Ginzburg-Landau without magnetic field also seems interesting. We're working on it now, but there are like some really serious bottlenecks that we have to pass. One of the main difficulties is that stability for Ginzburg-Landau in 2 dimensions is really not easy, and I don't think it's known in general. With a lot of extra assumption, it's not. Thank you for your attention. Any questions?
Well, thanks for the nice talk, Aria. Do we have any questions?
So I would ask, do you simplify something of KLA1 proof? With your methods, can some steps be simplified in the scalar case?
So yeah, like for example, there is also a Jacobian in the case of the Alencon, so you can just gradient u times the potential without the absolute value, and you can do the same things. And I think at least you would get the same result with the epsilon squared threshold. I think if you also mix this with quantitative stability for the ODE, you might be able to improve this epsilon squared a bit better. And if you also do this locally minimizing this picture that we constructed, you might be able to avoid that whole maximum principle type technique, because I know Kelly Wang at the end, he appeals to some kind of Gibbons conjecture that then he concludes that his methods can immediately give you the classification. So probably with these, you can kind of just bypass those, which I don't know if it would be worth to write down, but yeah, thank you for your question.
Maybe one more question. Is there any scalar quantity that you can create, like, right, there is this sort of proof for Allard regularity without in higher codimension without doing the excess, still doing the viscosity method. Would something like, is there like some quantity that like for example, the zero level set, does it satisfy some maximum principle with hyperplanes on some large scale or something like that?
It's a very good question. So we were actually banging our heads to the wall trying to get an equation for the ln of the modulus of this, or say if you just look at the modulus and you take the inverse function of the one vortex solution, there are so many extra terms that behave bad. That's for the question of satisfying some sort of maximum principle. There's another thing that I was writing down, is that if you slice, so if you think about the energy measure, and if you slice it, and if you test it with just x squared, okay, and if you think about this as a function on n-2 tangential directions, so basically it kind of mimics like the square of a harmonic function. In a weak sense, at least in the limit, this is going to be subharmonic somehow. It's something I wrote in a scratch paper, never really took seriously, but in some weak limit is going to be subharmonic in some sense. So I was also actually interested to see if you can actually do something like this, just avoiding all of Allard's machinery, something quicker for Alencon. Maybe it can be done, and the equations looks very similar to the Allard strong constancy lemma. So when you want to get so in Allard's in his paper that he proves some integrality, there's a paper that's very hard to obtain. You have to ask libraries to give you a print. That there is a lemma that's if you slice the energy measure, and if you just integrate it, there's a very weak equation that you can see. If you combine it with positivity and L1 infinity bounds, you get L1 precompactness. You can do something like this also, but if you test with x squared, something similar, but it's not immediate. It's still in the weak limit.
Okay, thanks.
You have any more questions?
Maybe just a quick question.
Uh-huh.
No, I mean, in higher codimension, cases, are there meaningful excess functions correspondingly, or only like it's the two excess function you consider only in codimension two?
So this is a very good question. So there are many difficulties in higher codimension. So one of the things is that to find an energy that in higher codimension approximates, like say codimension, for example, codimension 3 minimal submanifolds is not too easy. And one of the candidates that's we're actually talking with Daniel and Alessandro is the SU2 Yang-Mills-Higgs functional. SU2 Yang-Mills-Higgs functional. So you saw that in 2 dimensions, the solutions of these U1 Higgs or abelian Higgs are very well understood, right? But SU2 theory in 3 dimensions is a mess. So there are stationary solutions that are not minimizing, right? But still, you see that one of the main ingredients here was the self-duality, right? Which in Alencon is the ODE, the balancing of the Dirichlet and the potential. In abelian Higgs was the vortex equations, and in that SU2 you also get a self-dual regime, which in the gauge theory community they call it monopole equations, I think. And you can also do something there, but even the results before that are not known yet. So even trying to find, and in the case of just stationary points, it's wrong. I think you have to put some stability assumption for at least SU2 stuff. But really, it's the self-duality question. If you have the self-duality, somehow this machinery you would expect it to go through.
Thank you.
May I ask a question?
Yeah, sure.
Oh, without multiplicity one, that
Uh-huh.
is it possible to, I mean, in particular, for example, 1D and 3D to have some classification of the singularities?
So without multiplicity, so for example, if you go to very high dimension, even the integral currents, the theory is a mess, right? It's very hard to obtain it to this case. But in lower dimension, like for example, dimension 3, you would expect something like some classification to hold. And I would also be interested. To be honest, I've thought about it a bit. For minimizers, it should be doable. I don't know for stationary things, and for stability, it could be interesting. Because when you do min-max stuff, you know that the instability is focusing on some regions. So classifications of the entire solutions in 3 dimensions, at least stable ones, could be really useful. Could be useful for finding geodesics in dimension 3 at least.
Yeah, or 2D and 4D, yeah.
2D and 4D also, but can't you do like a catenoid and make it constant in the other direction? I think Gibbon's conjecture in 2D and 4D is also not true. Is it true? You can have codimension 2 minimal surfaces contained in tubes in 4D, right? That are not flat.
Yeah, but if it is not flat, but under some condition, can one say something about this? What are
Yeah.
singularities?
Maybe like stability. That could be interesting. But still, also the stability for this PDE is, at least at first glance, it looks very messy. The stability. So it's not as nice as the stability condition for example, Alencon, which is just like 2 terms. There's a lot of terms playing in the equation. I haven't played with it too much. There might be something there.
Yeah, thank you.
Thank you for the question.
Any other questions? I have one more. Sorry, it's not directly about, it's just a codimension 2 question. So it's not really about the
Uh-huh.
talk, but while you're here, I wanted to ask.
Uh-huh.
So there are graphical minimal cones of codimension 3.
Uh-huh.
Like there's this Lawson-Osserman
Uh-huh.
example. I'm not aware of any such examples in codimension 2. I was just asking you if you know if there are any special results.
To be honest, I don't know. Yeah,
Okay.
to be honest, I don't really know. So you're asking if there are examples of codimension 2 minimal cones,
Which are
at
graphical,
least,
yes.
which are graphical.
Right.
But I have never thought about this, to be honest. I don't know.
Okay. No worries. It's just...
Yeah, yeah.